the final thing I want to talk about this morning is what the service is going to look like for you as users of the system, right? This is our first heterogeneous Tier 2 system, but it's not our first heterogeneous system at UCL. I've already mentioned Myriad. We have a policy at UCL that we try, when we integrate things, we try to make it like the plumbing aspect of it slightly hidden from the user. So this system will be completely integrated into Young. It will use the same storage, use the same scheduler, and the way you will access the GPU nodes is by, in your job script, requesting that you have GPUs. You'll add a line in there saying how many you want. There's a slight technical hitch, which is I'm not entirely sure at the moment whether it's going to be GPUs per job or GPUs per node. We haven't entirely decided that yet. But when you add that flag in, it will route your job onto GPU nodes when it's run. There's another small technical hitch, which is, of course, as Nick has said, the GPU nodes have AMD processors in them. If your code is compiled with AVX512 on it, it will not work. So you need to recompile it down to AVX2. As well as that, we have spent some time putting together environment modules for the commonly used applications. So when you log in, VASP, LAMPS, NAMD, and GROMAC should all be available, ready to run on GPU with GPU versions. And all you'll have to do to use those, apart from adding the GPU, the line requesting a GPU, is load those modules instead of the ones you use currently in your job script, and it will run, no porting necessary. Of course, a big aspect here is we want to help, we want to encourage people to port their code over to GPUs. So we have a lot of development tools on the cluster. Some of these are things we already have the CPU variants of. Some of these are things we have installed for GPU on Myriad, but of course we're bringing over to Young. A big one that I think NVIDIA are going to talk about a bit later is we have the NVIDIA HPC SDK installed. I almost said a couple of years ago, but it's now many years ago, NVIDIA purchased PGI. If you've used some of the older national systems like Hector, which is Arch's predecessor, that used to come with the PGI compiler suite. NVIDIA has bought that and released a suite of tools based around that includes Fortran C, C++ compilers. It's free as in beer, so it's not open source, but you can download it and install it on your own machine completely legitimately from NVIDIA's website. And NVIDIA spent a lot of time enhancing, as you would expect from NVIDIA, being as they are a GPU vendor, they spend a lot of time enhancing the support for GPUs. So again, 5 or 6 years ago, when you wrote code for a GPU, you had to spend a lot of time writing it in CUDA, which is, for those of us like me who are very old-fashioned and like Fortran is a slightly annoying language, because it resembles C, and that's just the wrong thing. But they've spent a lot of time adding stuff like directive-based languages like OpenACC and OpenMP, so you can add directives to your existing CPU code and have it run on a GPU. They've got libraries like Nickel, which I think there's going to be a presentation on later, which makes programming GPUs very easy in parallel. And one of the things I really like that they've done is they've started looking at the features of the languages like C and Fortran that are inherently parallel, and started building stuff into their compilers that lets, when you write code using those constructs, will automatically put it onto a GPU. And a good example for us Fortran programmers is there's a thing called do concurrent in some of the later standards, which is basically do a loop, but the order of the iterations doesn't matter. And so that's a natural thing you can just farm out to any parallel system, but to a GPU, right? We have also, as part of the effort for this project, we thought it would be a good idea to trial the Cray programming environment, because NVIDIA's compilers do OpenMP and OpenACC on GPUs, as does the Cray one. We are in a slightly exciting position that HP owns Cray now and has done for a couple of years, which means that we are allowed to buy this and install on our systems. We haven't bought it yet, but we've got a trial of it, which we're deploying and testing. And assuming it is useful, we will purchase it properly for the cluster. It provides C and ++ and C and Fortran and all the things you'd expect, and a lot of really interesting performance monitoring and debugging tools. And then there are some of the non-traditional ones. I always try whenever I'm talking about HPC to people to shout out Julia, which is probably the least terrible new language that anyone has invented yet. It's a language targeted at scientific programming, so it's interesting to us because that's what we do. One of the nice things is because it's a new language, it exposes parallelism in a consistent way, whether you're doing shared memory or distributed memory programming. And more recently, it also does this for GPUs, and there are different libraries you can use with different levels of abstraction, from things like floops.jl, which lets you just say this loop runs on a GPU, all the way down to ku.jl, which is very much like writing CUDA, but with Julia syntax. And finally, probably the most popular language outside of the performance ones, Python. NVIDIA has put a lot of effort into producing plugins for Python that allow you to run your Python code, if not directly on a GPU, then calling GPU libraries. So they have versions of NumPy and SciPy that run on GPU. They have a slightly terrifying thing, which is you can use Numba to generate native GPU code. It's a bit odd, but it does seem to work. That's why there's a screenshot down there, because I tested it on Myriad last week and was faintly surprised to see that you can indeed write Python code, which then executes on the GPU. And there's also interfaces, there's some more common interfaces for interfacing CUDA from Python. The final prong in our getting you up and running approach is containerization. So for a long time, we've had containerization available on all of our services using a tool called Singularity, which is very common in HPC because it's Docker-like and mostly Docker compatible, but adds like better security to prevent users from messing with each other. That's sort of, up until now, that's been a sort of hidden feature of our clusters. If you needed to know about Singularity, we told you, and you went off and ran your stuff. As part of this effort, we're putting together some proper documentation, mostly because NVIDIA also offer a thing called the NVIDIA GPU Cloud, which is a service which has large numbers of packages built for GPU that you can just run. And that's what Singularity, and that's a good way of getting yourself up and running if it's a piece of software we don't provide. The final thing is actually Singularity is how we're testing the Cray programming environment, because the Cray programming environment expects to be on Red Hat 8, and we are currently on Red Hat 7. So we have built I think it might actually be a CentOS 8 rather than Red Hat 8, but a Red Hat 8 compatible container with the Cray PE, which is how we're testing it at the moment, and that currently is running on our systems. We have also, as various of the vendors will say, got support, quite good commercial, code porting and analysis support from both the vendors. HP and NVIDIA both have donated a lot of effort to this work. And HP are offering, as we've said, porting effort and optimization efforts. NVIDIA are also organizing training like today, and there will be future courses on how to use specific porting tools, and also work with their engineers sitting down with code developers from the community and helping them optimize their code. Delivery, I became head of research computing just as the pandemic hit. And so there has not been a day when I've not been in this post where there hasn't been something horrendous happening in the world, which has made it difficult to deliver these systems. So we had a really tight delivery deadline. We were notified of funding on the 24th of November, as I said earlier, and the hardware is, I believe, on a truck outside the data center now. And I got an email a few minutes ago saying that the truck had arrived. We are meant to spend the money by the end of today, which I believe we have achieved on that basis. But you'll have seen in the news, and you'll know if you've tried to buy anything computer related, there is a massive supply chain meltdown and has been for some time. Some of it is COVID. Some of it is that most of the semiconductors in the world are built by one company called TSMC, and due to the behavior of some of their customers, they scaled back production at the start of the pandemic, only to discover that actually there was a massive increase in demand. And so there's been a shortage there. And, we seem to have narrowly avoided global thermonuclear war, but when I wrote the slide, it was, not an unreal possibility. But the end result is that some parts have lead times of over 8 months, up to a year for some switches, not ones we're using, thankfully, but it's a real challenge to get this stuff. and HPE spent a lot of time getting us a design and getting the system through their build process and sourcing parts to get this machine delivered. So they spent a lot. They did some really, what for them might be considered risky things. So we got notified of the funding on the 24th, but we didn't have the money processed until January, and they actually started the build sometime before Christmas. So they took that risk on, and that was we're very grateful for that, because we would not have delivered it without that. And they spent a lot of time, prioritizing the shipment through their process. So I'm going to hand back to Tim to talk about the Cray PE, but I'm happy to answer any questions in chat. So please ask.